Hello YouTube. So this is one of my two video lights I use for filming my videos. When I was filming my last video about disassembling a Keithley 160 digital multimeter, at the end I started noticing a little bit of flickering in my lights. So with the first of these lights I bought, I noticed after half an hour of use that the light got very hot and started dimming down for a couple of seconds and then going back to normal. And this repeated every 1 or 2 minutes. So on my first video light, I actually went to modify the casing a little bit so it got more air without using a fan, so that the light didn't overheat anymore. At that time, I was using the light completely as a downlight, so the airflow was restricted in the electronics section by the casing of the electronics, and I noticed that in this area you see this rectangle. There's actually a piece of plastic glued in here from behind, so this is not complete molding. The rectangle inside here is separate, so my guess is that this is a position for another kind of switch. So on my other light, I removed this plastic part and I glued a grill in this position, so there could actually go airflow through here. And also on the voltage regulator or the current regulator for the LEDs, which sits under here, I stuck a small heatsink on it, so it gets a little bit more of cooling, and this resolved the overheating issue for me completely. So when I bought the second light, I bought it because I was planning to illuminate my desk more from two sides and not from the top. I didn't have this issue, so I tested it. I let it run for hours in the stressfulest position I could imagine, and it didn't dim down. So I thought, oh, okay, maybe only the first one was a little bit out of spec or had some kind of an issue so that it started overheating. And I thought, okay, maybe the second one is better, or they changed something. This doesn't seem to be the case. The video light doesn't shut down or throttles the LEDs down. It just started failing after a couple hours of runtime, and because I think these are reputable LED lights, I'm just wondering why they are failing. So on this light I have the problem that it starts flickering, and now that it has started to fail, it starts flickering after a couple minutes of runtime. And I just want to find out why, what is failing. And also I notice a smell coming from the device, so I think there is a component burning up inside of the casing. Also, after placing it on the desk, turning on the video lights so I could film this, I noticed that the casing or the front panel seems to have melted down a little bit in this section here. I don't know if I can show you this, but in the corner down here there is a clear deformation that shows up in the light. So I noticed that not only the front panel of the LCD, but also the switch and the casing around the switch have deformed a little bit. I don't know if you can see this in the camera view, if I am correctly in focus, but it's all a little bit deformed around this corner. So I just took the mounting bracket away and we can start with the teardown. So in case you are wondering, yes, there was still warranty on this product, but I thought I'm curious and you might be curious too. So this is the inside. Oh, yeah. There are two battery holders and they are just falling apart. They have this little plastic pin, a plastic pin with a spring. I might get this in focus. Okay, I have. So that fell out. So then there is interesting wiring. So these are just connectors to, I think, different LED strings on the front panel. Maybe I should show you the front panel. Okay, that's the back panel with the electronics. These are the 900 LEDs in this video light. There are two groups of LEDs, warm white and cold white LEDs. They are arranged in, I think, lines going from one corner to the other corner. So diagonal lines, and they are used to regulate how warm or how cold the color temperature of the light you want should be. So when you turn the knob on this electronics board, or you use a phone app which connects via Bluetooth, you can change the color temperature of this light. I think it's also available as an RGB version, but I don't need colored light. I just need good white light. So I thought it might be a better idea to get an only white video light. So this is our electronics assembly. Let's just try to find out how to get this apart. Oh, that's an interesting construction. What did they do down here? So there are different cables, and on the middle pin of the switch, there is a copper rod or a thick piece of copper wire, and it has heat shrink on one side and it's just hanging around on the other side. Hey, what did they do here? I don't see a reason for this thick piece of copper here. Did they... So here is the area where the current regulator is placed. So maybe they used this copper piece to transfer heat away, but I can only guess. So this is a strange construction. I can't say more. It's just a little bit strange. So let me try to get the main PCB out. Okay. Yeah, it's held down by this copper piece now. Okay. Let me just grab the soldering iron. Let me just try to get all the wirings and this strange copper piece out of the way. I'm really wondering if they used this to fix the PCB in place, or if they really tried to use this as kind of an heatsink. It's strange. It's just a piece of copper, bare copper, and a piece of heat shrink tubing so that it won't short to the PCB. Hell, that's strange. Okay, this wire might stay in place. Okay, what's that? Okay, the red wire looks like a positive terminal. In the battery compartment there's no marking, but if you look closely on the PCB, in this section there is clearly marked battery negative, battery minus. So I really don't know what's going on here. Okay, there's a DC plus, there's a V plus. Strange. Okay, let's just try to get the PCB out here. I did forget to desolder the red wire. Okay, can I get this out now? Something is not... no, I have to pull this knob off. Maybe it was the knob. Okay, there's our PCB. Ooh. Oh man, that burned down. Whee! That really burned. You see this I see down here? It has a clear burn mark. And okay, I think this crustiness around here is mostly flux. But when you look at the pins and you look on the IC, it has clear burn marks. And I think this white dot on the IC might even be a point where I can, yeah, okay, I can rub this away and I can stick my tweezers in there. So something burned itself free. So that chip is clearly dead. As far as I know, it is used to switch between the cold white and the warm white LEDs. So it is not directly responsible for creating the current. The current is created by this IC down here. It's an LED driver from XL Semi. Seems to be a not so well known brand, I guess. I never heard from them before. Yeah, but I think, yeah, maybe. So this is the position. The PCB sits inside the light when the light is in use. So I think the heat from the regulating IC rises up on this PCB and in the air, and then this small IC which somehow selects between the different color temperatures gets too hot, and at least in my case it melted down. Perhaps there's also another failure point. Perhaps the LEDs drew too much current, but then the overcurrent protection should be reacting on that. I really don't know. The only thing I can see is that the left two and the right two connectors for the LEDs are separated. So they are switched between by this IC. So I think I should, okay, maybe this is a kind of a MOSFET. I think I should get a data sheet for this. But it seems that on the right side there are the upper 2 or 3 pins are connected to digital signals, and the lowest pin on the right side, or pin 1 I think from the markings, is connected to these 2 resistors and then gets fed by the LED driver. And it may be that there is just a switch channel from the input to the first or the let's just say the cold white LEDs, and also a way to switch from the input to the second set of connectors, or the warm white LEDs. Did I say warm white and warm white? No, I mean cold white, warm white, or vice versa. Which one is which, I'll need to find out. But this switch burned down, and at least one channel is broken and the other channel is soon to follow. So I'll need to get this IC replaced, and then I'll start modifying this LED light to make it more robust, or give it a little bit of a better cooling and a chance to hopefully live a long life. So I desoldered the IC and looked up on the internet what kind of an IC this is. And yes, this is a dual channel MOSFET, which is used to switch the incoming power, the positive rail, which is on this this PCB plane, goes through the connectors to the LEDs, and after that goes through this MOSFET to ground again. So both this side here are the cold LEDs going through the MOSFET to ground. This side here is the warm LEDs going through the IC to ground, or not to this ground, but to this ground. And both MOSFETs are switched using these 2 connections. And you might be able to see that the PCB trace here is a little bit darker than the rest of the PCB trace. And also this copper plane here on both sides of the IC is darker than the positive copper plane here. So this copper plane got very hot, and the solder mask on the PCB discolored because of that. And also you might be able to see that this lovely little 2-channel MOSFET IC has a little burn hole. And also when you look on the other side, you might be able to see that it has deformed a little bit. So this is clearly, it's still working on one channel, but this is clearly a broken N-channel MOSFET IC. So I'll throw that away and try to get a new one. And what I found out when I looked at the PCB more closely, there is written on where the warm and the cold LEDs go. So this might make it easier for me to put this back together when I can fix it. Also, someone put on to for which products this PCB will be used. So it's used for the Lumen Panel 600 and 900. So it might be that for the 600, which has a lot less LEDs and so a lot less power, this controller is sufficient, but it seems that it is a little bit underrated for the 900 LED model. Because, yeah, it's the second one that failed on me. It's okay. The first one didn't fail. It just turned down the power, but okay, for me, for a video panel that should be used over hours, that's failing too. It shouldn't overheat. Not for professional or semi-professional video equipment. It should not overheat. It should not have a problem. Through the magic of video editing, I have here an old component and a new component for you. So let me just show you how I selected the new component. First option would be to just buy the same component, but on the suppliers I used, I couldn't find it. I could have bought it in China, but I didn't want to wait. So I just searched another component that fits the needs of this device. So I just want to show you what I looked for. So first, an obvious most important choice was to look out for the inner structure of the component so that the connections are the same. So on this component you can see there are two transistors inside. Both transistors have their drain connection on the right side of the IC doubled. So two connections per drain. And the sources and the gates are on the left side of the IC, or the IC package, because I would call this a transistor, not an IC. Not just because it's in the package of an IC. So the only difference I can really see is that Alpha Omega plays the what they call the second transistor on pin 1, 2, 8, and 7, and the first transistor on 3, 4, 5, and 6. And Rome did it the other way around, so they called the transistor on the first 4 pins of the IC package transistor 1 and the other one transistor 2. So that's not a problem. But you can see, if you look into the list, then pin 1 is the source, pin 2 is the gate, and the same for transistor 2. There's 3 the source and 4 the gate. And on the opposite side, 5 and 6 are the corresponding drains, and 7 and 8 are the corresponding drains for the first transistor. And that's the same on the Alpha Omega transistor. they have first the source, then the gate, and then again source and gate, and the drains on the other side. So from the package and the pinout, the components are the same. So then let's take a look at the other specifications. The drain source voltage is the same on both packages with 30 volts. Then the current each transistor can handle is a little bit higher on the ROM part, so there isn't any issue for us. And then we will go a little bit into the details. So next thing on the alpha omega part is the gate source voltage that is allowed to be plus minus 12 volts, and on the ROM part it's plus minus 20 volts. So the ROM transistor can handle a little bit higher gate source voltage. That's good for us. At least it's not a problem. A lower gate source voltage might be a problem, but I'm guessing that the gate is only driven with plus 5 volts. So even a transistor package with a lower gate voltage would work. But we don't need to look closer into the circuit if we have to change something or just use another component. The gate voltage is higher, so that's okay for us. I don't know if this transistor is used in its linear region or just as a switch, but I'm guessing it's just used as a switch. So interesting for us would be the resistance at different or the current rating at different gate voltages. We can check that later. And the gate charge. So if we use a transistor with a lot higher gate charge, it might be a problem when charging and discharging the gate of the transistor, which might lead to a not fully switched transistor, and due to that to higher losses in the circuit and burning up of the transistor. What's also interesting is what power dissipation is allowed in the package. So the original IC or transistor has an allowed maximum power dissipation at 25 degrees C of 2 watts and at 70 degrees of 1.3 watts. So we don't want to go lower because that might lead to a transistor that's burning up. And we've seen that that transistor has burned up, so it got too hot. That might be the reason of a broken part, or that might be the reason of bad thermal management. And so it seems to be, from what I saw on the PCB, that the IC was a little bit used on its limits, so we don't want to go lower. In fact, on the top of the datasheet, it mentions 3 watts, but that's only valid to about, where is it? So when we look here, there is a 1, a 4, and a 5. So 1 is on a ceramic board, so special circumstances we don't have here. We have a normal PCB. Okay, mounted ceramic board, mounted to copper board, but okay, this doesn't list the an environment temperature. Okay, it lists the environment temperature here. Is this valid for all measurements? So 1.4 watts would be a little low on a copper board. Okay, we'll see if it burns up. I don't think so, because it has... Oh no, it has the same temperature ratings, junction ratings. So do we have thermal dissipation ratings of the package? Yeah. There are they. For the others I see. I don't see them. Oh, there they are. Okay, they are quite similar, so we don't have an advantage there. What do we have next? We have the resistance at 4.5 volts. That would be most interesting for us. That's a little bit higher. Okay, but measured at another at a higher current. Oh, that's quite complicated to compare. But I think that should be good. That should be still good to go. Where is our capacitance? Input capacitance. Total gate charge. That would be most interesting for driving this transistor. So there we have a little bit, when I see it correctly, 6 to 7 nanocoulombs at 4.5 volts to 7.9 nanocoulombs. It's a little bit higher, but I don't see a problem there. Then we have the characteristic curves. So here we have what I'm most interested in, the characteristic curve of the drain source voltage against the drain current when there are different voltages applied to the gate. So you can see here there is a curve for 2.5 volts, 2.8, 3 volt, and the 4.5 and 10 volts are all on one line. So you can see that the gate is starting with 4 volts is quite completely saturated. There's not a lot happening there. But before that, between 3 volt and 2.5 volt, there's a lot happening. And on the alpha omega transistor, it's the same, or not quite the same. It's I think it has more resistance there when it's not fully saturated. Looks like, but okay, it's hard to compare. They have different scalings on the ampere range. So when I look at a gate source voltage of 2 volt, I can shove 10 amps through this transistor and it doesn't even go above 1 amp. And when I look for the Rohm transistor, I don't even have an 2.0 volt gate source voltage. Okay, but I'm expecting the Videolight to use 5 volt, or what would be more common due to losses would be a gate source voltage of 4.5 volts. So we have a little bit too low resolution in this area, so we can go to this chart, which has another scaling on the drain source voltage. There we can see that on 4.5 5 volts, we have this line here. And on the alpha omega, we have this line here. Didn't quite hit it. So when we want to compare it, due to the scaling, can go a little bit under 10 amps. And we can see here, I think this would be around 0.2 volts voltage drop. And when we look on this transistor, we are on around 0.15 volt voltage drop. So the resolution of this graphs isn't good enough to exactly find out what power dissipation we would have on this transistor, because you could just go in and now say 9 amps against 0.15 volts are a couple of 100 milliwatts power dissipation. That is okay for the casing. We have 2 transistors. We need to multiply this by 2, but I'm sure we will be within the limits. So this transistor should be good enough for us. I'll just clean up that spot a little bit and free it from the old solder. Oh, I need a lot of heat there. The copper is sucking the heat away very good. Okay, that looks nice. And now, with a little bit of fresh solder, we will place a new component there. Okay, the placement looks good. Now to the rest of all the pins. Done, nice. So a little bit of cleaning left to do. And then we can go to testing the device. So let me just clean the new solder connection. And after that, I will just try it out and look if it works or if it blows up. We have still the problem that we don't know which one of these wires is for which color temperature. So I'll just try to figure it out. I have here this lovely multimeter. Wait a moment. This one here. And it's not only capable of doing a diode test, but it is also capable of doing high diode test at high voltages. So when I press this button now, it switches to 15-volt diode test. And I think that might be enough to drive these LEDs. Yeah, I can see them. Might be cold white. Next one. Okay, I see them. Cold white, perhaps. Let's compare them to these cables. Okay, that is clearly warm white. And the other one too. So that's warm white. And that should be cold white. Yes. Okay, so we have warm white here, cold white here. I'll mark them and we can proceed with testing. Give me 1 second, I will just build that up for you. Okay, this might take a little bit longer. Okay, I'll have to look up where they... No. This comes from the power jacket. Goes to the other side of the switch. The switch just alternates between power jacket and battery. And this cable is the power of the circuit, and the switch just decides from which power source the circuit is powered, or if it is even powered. So I might have to place this unknown contraption here again. Which might have to do with cooling, but I'm not sure. Okay, that's in place again. And then the power cable. But I'm only putting it together for testing. I want to make thermal images of it overheating. And then I'll modify it with some heat sinks and a little bit of more airflow. And after that, we will make a new thermal measurement and watch out for the if the case no, I have not mixed them up, if the case stays cooler after modding. And if the case stays cooler, then the electronics should be cooler too. Those pins are working? Okay. So I don't care where the arrow on the knob points to, because it doesn't have any reason to be there. The rotary encoder has no orientation. So let me just grab the power cord and hope that it doesn't explode on me when I try to turn it on. And there is light, and all LEDs are on. Nice. So I'll just add the bracket again and let it heat up for a while, and then I'll make some thermal images of it, or I'll make a thermal imaging video of it to show you where are the hotspots and to hopefully be able to compare them to the modifications I'll do to this video light after the initial measurement. So the LED light has now been running for around half an hour, and I'll just try to show you the heat distribution on the casing. And you see the display in the middle, and when you try to remember where the components were placed, you see that the hotspot is right there where the LED current driver was placed. So you can see that this has reached around 54 degrees after half an hour. And that is also the spot where I showed you in the beginning of the video. The front plate of this casing has bent a little bit due to the excessive heat. Okay, I'm showing you around a little bit. So I'll just turn the video light around. So there we see the LEDs, or we don't see the LEDs directly. You can see that there is a hotspot on the top of the video light, and directly under this hotspot it is a lot cooler. But that's not correct. It's only that the that I have the plexiglass sheet on the front of the video light, and that is not conducting the heat or letting the infrared emission through. It's only letting the visible light through, but not the infrared emission. So I'll take that off. And then you can see the real heat distribution. And it looks like that there's also a slight hotspot where the electronics and especially the LED current driver are placed. Follow the hotspot, and there it is. So next we'll look into a way to reduce the heat inside of the electronics housing of this video light. So I've just taken the casing apart and pulled out the electronics, and that took me around 4 to 5 minutes, and you can see the electronics are still very hot. Around 40 degrees on the on the LED current driver, and you can see that the heat traveled up into the direction of the display and heated the display up with it. By the way, the new MOSFET we put onto the PCB seems not to have heated up in any form. It just looks like the PCB. It seems to have exactly the same temperature. There it is. So, like I showed you before, this case has a spot where an unused component could be placed, and this spot is prepared inside of the molding of this case, but has been glued shut after that because it was not used. And I want to reopen this and glue this metal mesh, which is stolen from a broken smoke detector, and glue it in place around here so that the hot air can go through, but nothing falls inside of the case, or no one can touch components inside there, because it's a low power device, but it's still an electrical appliance, so we want it to be at least a little bit safe. And I think that's the moment to remember you that everything I do here and you repeat at home or wherever, when you repeat it, you do it on your own risk. Remember that. Okay, let me just try to get this. Can I pick that glue out? No. It's glued in here quite heavily, but maybe I can just push it through. No. Okay, it starts to move. So we don't need this plastic part anymore. There's still some glue left. I'll try to get that out. Okay, I think that doesn't need to be very clean because we won't see it anymore. But if you try to repeat that, then you can do a better job if you want, or just leave it so. So next should be this PCB. So before I can stuck this heatsink on the LED current driver, I need to make sure that it is free from any contaminants that could make the glue not stick to the surface. So, and if I just glue this heatsink down here and then try to put the thing back together, I might have a problem because there are components in the way, like this switch. So I'll just try to put it back together. Perhaps I'll also put some of the screws in there. And then I'll try to put the heatsink on from the outside. And I can do this because I did not put the mesh on there again. So can this heatsink fit? I'm not sure. It cannot fit greatly on there. There's a piece of plastic in the way. Perhaps I need another heatsink. What heatsinks do I have? I still have these Raspberry Pi heatsinks. Could this be a match? This could be a match. This could also be a match, but it doesn't have as much area as the bigger one. So I might need to clean the hole up a little bit more to get the bigger heatsink in. Because the only collisions I could see were with this glue that's still in here. So I won't get around cleaning this. And after cleaning, I'll put on the heatsink. Okay, that looks good to me. Okay, this looks like it will fit. And there is the heatsink glued onto the LED driver. It has a little bit of space to breathe on the top and the bottom, but I think most of the heat will be dissipated by radiation and through the metal mesh. Looks good to me. So next up will be getting this mesh to fit. So I'll just cut a piece out of this mesh and then gluing it in place. That should be straightforward, I hope. There's our piece of mesh. And it fits in there. So let me just clean that area from any debris, and then I'll try to glue the mesh in place. So what I have here is quite an old tube of silicon, high thermal silicon I used for my 3D printer. One 3D printer I built a long time ago and it didn't work very well. Thanks God I have a Prusa today. And I hope it's still good. Is it? Doesn't look good. Maybe I have to skip the silicon. It smells a lot, but it seems to be hard. Okay, not fully through. There might be a usable silicon left. Okay, I think I'll be full of black, disgusting silicon when I'm done here. And my tools will be full of that too. Still not good. Looks like fun, doesn't it? I mean, it's high temperature silicon, so it's the right tool for the right job, I guess. This could look nicer. But I don't have a nozzle for this tube anymore. So I need to get creative with distributing the high temperature silicon. Okay, at least it's glued on there somehow. And it's still a mesh. You might be able to see the heatsink through there. So there should be air movement through the mesh. And I hope that will do the trick. So I'll just put everything back together, let it dry a little bit, and then we'll see if it gave us an improvement over the last temperatures. So it's now half an hour later, and you can see, okay, it didn't get colder, but I think what we see is the heatsink through the metal mesh. So the heatsink is clearly hotter than what we saw before, but before we couldn't see the heatsink, but or we couldn't see the component which didn't have a heatsink. Now we can see through the case because we have a metal mesh there. You can see 57 degrees, but the casing itself, okay, now it reached 54 degrees like the casing before, but you can see the component itself can dissipate the heat a lot better. So if the casing would be closed, the heat we would see would be lower than what we can see now, if you know what I mean. And is the other side as cold as before? As hot as before? No, I think it got even hotter. Okay, makes sense. It's really hot today, and my lab is under the roof, so it is. I'm really sweating now because it's really hot in here. So it makes sense that the LEDs are even hotter now. Man, they're close to 70 degrees. So you could tell, you can really tell that the heatsink does its job, because it would be even hotter now that the LEDs are on 70 degrees. Okay, I hope you liked this mod and this repair. So I hope to see you again next time I upload a video. Please comment, like, subscribe, all the good stuff, and give me a thumbs up. And I hope to see you again soon. Thank you for watching. Have a nice day.